Good afternoon, everyone. I'm Amila Jayasinghe. I'm a PhD candidate at University of Cambridge. Today, I will show you how to minimize embodied carbon of reinforced concrete beams. So the global production of concrete is over 10 billion cubic meters per year, and that is responsible for around 8% of total carbon emissions due to human activities. So we structural engineers have a responsibility to do something about it. There are several things we can do about it. We should think of ways to reduce carbon intensity of concrete as a building material, and then we should think of ways to reduce the amount of concrete we are using in building construction, and also we should think of ways to reduce the amount of construction activities we need. My PhD focused on element optimization, and today's presentation I will talk about beams. Let's say we have a simply supported beam with an uniformly distributed load. The bending moment and shear force profiles would look like this. Conventionally, we are used to construct beams in a rectangular prismatic shape, but is that the optimum shape for these loading conditions? Instead, we can shape optimize the beam so that we will place concrete only where it is necessary. With We can realize these kind of constructions using flexible fabric formwork. Previous studies have shown that it is possible to reduce concrete consumptions by up to 40%. Let's say we are going to design a beam for a given load and a span. There can be so many viable design options. If we are talking about prismatic beams, there can be several choices for the design depth. Accordingly, we can calculate the amount of flexural reinforcement needed. Likewise, there can be several choices for the design width, and depending on the sectional dimensions, we can calculate the shear reinforcement along the beam. But when it comes to shape optimized beams, the picture is a bit more complicated. Let's say we are going to design this beam for a selected mid-span depth. We can calculate the amount of flexural reinforcement needed there and continue it throughout the span. After that, we can design several sections along the beam for a range of depths and widths. Each of these design will have a different amount of concrete and steel. That means different amount of embodied carbon. Therefore, searching in this design space would potentially identify the design with minimum possible embodied carbon for the selected design criteria. So this is the basis of the optimization algorithms I have developed in my study. I have developed three optimization strategies. First being the theoretical optimum shape finding. There I will find the geometry of the beam with minimum possible embodied carbon for the given design criteria. Since the outcome of such an approach can have problems in terms of construction and also sometimes even in technicality, I will talk about feasible optimum shape finding. There I will fix the depth profile to be parabolic, but the shape of parabola will be changing. To facilitate a fairer comparison, I will optimize prismatic beams as well by designing for a range of depths and widths. In order to compare these approaches, I will design beams for one span length, and I will optimize the beam designs using these three optimization strategies. To understand the effect of design load on the outcome of each strategy, I will use three load cases. Also, I will talk about two possibilities for the minimum possible width, because depending on how thin the beam can go, the outcome of these optimization approaches can change, as you would see. Finally, I will compare the outcomes with the conventional designs, which are based on conventional span to depth ratios and aspect ratios. This is the variation of embodied carbon with depth at mid-span for those three different load cases for three different optimization approaches. Also, you can see the conventional designs up there. Further explaining what this graph means, if we talk about the designs with the depth at mid-span at 700 millimeters, all these designs will have 700 millimeters at the mid-span as the depth. But in each case, the beam has been designed for the relevant load case and has been optimized using the relevant optimization approach. So these triangle points are the minimums of each curve. That means they show the optimum depths at each case. As you can see, even if the span and the load is the same, optimum depth for 3 different optimization strategies are different. Also, if we compare through the different load cases, you can see that the optimum depth has reduced with the load. This analysis has carried out assuming the minimum possible width is 200 millimeters. In reality, these parameters can be governed by either 5 criterion we decide or even the spacing of reinforcement bars. If we assume it can go even thinner, I have repeated the analysis here using minimum possible width of 150 millimeters. As you can see, the optimum depths, optimum designs have depended on the selection of minimum possible width. This graph shows the outcome of theoretical optimum shape finding for 3 different load cases for 2 choices for the minimum possible width. As you can see, even if the span is the same, the optimum shape has depended on those 2 criteria. The problem here is the outcomes from theoretical optimum shape finding has resulted the depth profiles to have positive and negative curvatures. This is not only challenging in terms of supplying the reinforcement in practical terms, even if we supply the reinforcement somehow, when the reinforcement is tense, there will be an increased shear demand. That is why we have to talk about feasible optimum shape finding. There also, as you can see, the optimum shape has depended on the design load case, and it has depended on how thin the beam can go. So let's talk about the possibilities of savings the embodied carbon compared with the conventional design. If we look at load case C2, the theoretical optimum shape finding can reduce embodied carbon by 35% from conventional design, but this can have some technical and practical problems. Therefore, the feasible optimum shape finding can still reduce embodied carbon by 31%. But more importantly, even without shape optimization, just by optimizing prismatic beams, we can reduce embodied carbon by 26%. From that point onward, feasible shape optimization can reduce embodied carbon by 7%. Now, this can sound a little bit contradictory because shape optimization is supposed to reduce amount of concrete used by up to even 30 to 40%. But the trick here is the optimum depths for prismatic beams and shape optimized beams can be different. Therefore, this 7% doesn't represent taking some amount of concrete from the same beam design. So let's compare the savings of embodied carbon for 3 different load cases. The optimum prismatic beams can reduce embodied carbon by 24 to 32% from conventional design. From that point onward, theoretical optimum shape finding can reduce embodied carbon by 11 to 13%, since that can have some challenges. Feasible optimum shape finding can reduce 6 to 8%. In all these optimization strategies, I have not based on conventional span to depth ratios for deflection control. So we have to check the deflection as well. So this graph shows the deflections under quasi-permanent load compared with the conventional benchmark. As you can see, the identified optimums can satisfy the conventional benchmark. So these optimization strategies have not violated the serviceability criteria. So I would like to conclude my presentations with these points. We can reduce embodied carbon by exploring the design space, but the optimums will depend on the design load and depend on how thin the beam can go, even for the same span. Shape optimization can reduce embodied carbon by up to 35% from the conventional design, but more importantly, even without shape optimization, optimizing prismatic beams alone can reduce embodied carbon up to 30%, and these presentations can even go higher if we assume the beam can go even thinner. Thank you for listening. I would like to acknowledge Dr. John Orr, Professor Tim Eibel, Professor William Boshoff, and finally Cambridge Trust for their support. Thank you for listening. I'm happy to take your questions and comments.
Thank you for that very interesting talk. And clearly, you know, given concrete, I think you said 8% of global emissions are relating to concrete, a very, very worthwhile area. There's a few questions popping up already in the chat. If I can go to Glenn, one of my fellow judges first.
Thank you for that talk. It's very good and relevant to the challenges we as an industry face today. I'm very interested to understand if you've started to think about how we as an industry, as a contractor, as a design consultant, start thinking about adopting this type of approach when we consider codes, reinforcement detailing, the way we go to work to build. Has that started to become part of your thinking in the development of these ideas?
I would say yes. I think with the precision we need, these approaches are much more suitable for precasting, and I think it is really possible with limited amount of resources to go into these kind of approaches in the industry.
Glenn, does that answer your question?
Sorry, I left myself on mute. Yeah, I think I agree with that. I'd be interested in your thoughts about are there any barriers to adoption from a code perspective, or do we need to think about updating, Euro codes to take this on board, things like that?
Well, that is tricky. I think the calculations I have used in my research are based on previous findings, which has been validated with experimentations, but also based on the basics given in, let's say, Eurocode. So I think we can safely go into further details for the construction activities. I think it is possible. I think there are no exact barriers of using this as long as we meet the ultimate limit state requirements and serviceability limit state requirements.
Thank you.
Thank you.
So next question, another judging question from Eleni, please.
Hi, thank you for the presentation. My question is related to what do you think are the construction manufacturing challenges for if we have to adopt this kind of shape optimization approach?
I would like to say, rather than challenges, we would need the know-how about the detailing of the formwork, because we can have very good precisions with the flexible fabric formwork, but we have to know how it would work, how the fluid pressures would work, how to arrange the reinforcement, and then how to arrange the fabric as the formwork. I think if we know how to do that, we can adopt these techniques safely in the construction as well.
Thank you.
Thank you.
And another judging question from Dennis. Sorry, Dennis, if you'd like to unmute.
Yep. Have you considered the sort of robustness standpoint, because clearly normal beam might not have critical sections like yours, and at the thin section, you might end up with sort of bending shear critical failure in combined actions. So is that something you would consider?
Yes, these designs are based on the assumed load envelopes. We have to further think of the accidental load envelopes we are going to consider, and depending on that, as an example, if we can get the envelope of bending moment and shear force, then we can design each section to withstand that expected load. In that approach, I think we can eliminate that kind of risk of having weaker sections.
Thank you.
Thank you.
And there's a few more questions in the chat. I wonder if I can summarize a bit. Michael and Edward, and actually something that I was thinking myself is how have you accounted for the carbon and the complexity around the formwork and the extra work that you might need to do on site? And is that in the figures already? Have you made an assumption that is quite small? And how did you go about sort of tackling that issue?
You mean the carbon intensity of the construction approach, I guess?
Yes. Yeah.
I think in that terms, this would be a bit beneficiary in terms of the conventional formwork as well, because we are going to use a fabric, and that is also reusable, and also the amount of force work we need, as in the timber force work, we can reuse more than the actual formworks as well. I think in that terms, we can safely say that this kind of construction techniques will have lesser environmental degradation impact compared with the conventional timber force work and formwork.
That's really interesting. And just aware of time, and I suppose the one thing that is burning question in my mind was, does the V bar take the shape you need, or do you have to bend it, or does it just sag to the right
There
shape?
are two things about that. We can use steel reinforcement bended in that shape, but if it is challenging and if you are going for much more complex shapes, we can use flexible FRP bars. And I think in my group, Dr. Jono has worked on those things. Like we can use filament winding techniques and bespoke the reinforcement cage as well. So there are several options we can adopt for these kind of construction techniques.
Thank you. Because it sounds like some practical things that could be done today, and some really exciting things for the sort of medium to longer term. Lots more questions coming from the chat. I'd encourage people to stay on for the networking at the end, and I think we'll have a topic. And actually probably topics relating to many of the talks we've heard, so we can continue the discussions and get to grips and have some time to kind of discuss the other sorts of questions and things that are coming up. So I'd just really like to say thank you, Amila, for your work.